All right, so we're going to do a quick exploration, and there might be various points where I ask you to pause and try things, so I think it's important for you to get a handle on what's going on. So this exploration has 3 parts. Number 1, show that a to the x for a is greater than 1 grows faster than x squared as x goes to infinity. I think this is fairly straightforward, right? You can set it up either way. If you want a to the x to grow faster than x squared, right? When I set this up, what I'm hoping is my answer is infinity, because that would make the a to the x grow faster, okay? Clearly, if you quote-unquote plug in, you get infinity over infinity, which makes you L'Hopital eligible, okay? I think there's not really anything hard about this, but I will mention that I think a lot of you probably are rusty or don't remember the derivative rules for a to the x, okay? And if you can't take a derivative correctly, then obviously L'Hopital's isn't going to go so well. All right, so as a reminder, the derivative of a to the x is natural log of a times a to the x, okay, and then obviously on the bottom, 2x. I'm still infinity over infinity. So I'm going to do L'Hopital a second time. Remember your limit statement. Okay, on top, natural log a is just some number, so it's a constant. So I'm not going to worry about that. And if I take the derivative of a to the x again, it's another natural log a times a to the x. And so what I have here is natural log a, that quantity squared, times a to the x, because 2 copies of that times a to the x. And then on the bottom, I have 2. So if you quote-unquote plug in, again, you're doing infinity divided by 2, which is infinity. And I would say your final statement, maybe something in words explaining your answer. So therefore, a to the x grows faster than x squared. Okay. For problem number 2, or exploration part 2, show that 3 to the x grows faster than 2 to the x as x goes to infinity. Take a second, just pause and see if you can set up and see if you are feeling stuck or not. So take a chance or take a try to see if you can figure out what's going on here. All right, hopefully during your pause, right, you set this up, okay? And then you kind of thought about the fact that if you quote-unquote plug in, you're getting infinity over infinity, which makes you L'Hopital eligible. So if I apply the rule that we just learned or reminded ourselves of, the derivative of 3x would be natural log of 3 times 3 to the x. Derivative of 2 to the x would be natural log of 2 times 2 to the x. I get infinity over infinity. Okay, well, let's just do L'Hopital's again. Okay. If I do that, on the top, I'm going to have ln of 3 quantity squared times 3 to the x over ln of 2 quantity squared times 2 to the... Do you notice that this is the problem that is not changing? No matter how many times I take the derivative, right, with L'Hopital's, I'm never going to fix that problem because that's always a part of the derivative. And so this approach actually does not work. Okay, so this doesn't work. So does it mean that we can't do it? Of course not, right? What it means is we need to be a little bit clever. And so what I want to show you is sometimes it's helpful to do a rewrite. If both the top and the bottom have the same exponent, then this is equivalent to the limit as x goes to infinity of 3/2 to the x, because of the way exponent rules work, right? If you have a fraction, that exponent goes to both the top and the bottom, right? But now this is just exponential growth, right? Because this value is more than 1. And so if this is exponential growth, then my answer is infinity. And this means in my original setup, so right here, okay, that means the top function is growing faster. So my conclusion would be, therefore, 3 to the x grows faster than 2 to the x. Okay. All right, so sometimes you got to be a little bit clever. Okay. For the third part, show that if a is greater than b is greater than 1, show that a to the x grows faster than b to the x. Okay. All right, so again, if I put a to the x on top and I'm trying to show that grows faster, I'm hoping that the answer to this problem is infinity. Okay. And so I'm going to use the exact same trick we just used in part 2. All All right, and then I would say we do need to make sure we know, is this number bigger than 1? Because if it is, it's exponential growth. If it isn't, it's exponential decay. All right, since A is greater than B, that means that A over B is greater than 1. Okay, and so we know this is exponential growth, therefore it's infinity. So therefore, A to the x grows faster than B to the x when A is greater than B is greater than 1. All right, so the next one asks you to compare, right, a couple of functions. It says show that ln x grows slower than x, okay, to begin with. So let's do part A. If I want to show it grows slower, I certainly can set up my limit so that it's on top, right? If I do that, growing slower, I want the answer to be 0, so that is my hope. Okay, if I do my initial plug-in, as x goes to infinity, natural log of x continues to grow just super duper slowly, and so I get infinity over infinity, which makes me L'Hopital eligible. Right, and this would be 1 over x over 1, or just 1 over x. And if I quote-unquote plug in infinity, right, 1 divided by something really, really big is really, really small, and so the answer is 0, so therefore natural log x grows slower than x. Okay. All right, for part B, show that it grows slower than x squared. Well, my hope is that kind of makes sense just from like thinking about it, but we can do pretty similar situation here. Okay, this gives me L'Hopital eligible. Okay, if I take the derivative, 1 over x over 2x, and this is a case where I think it makes sense to spend a second and algebraically simplify this before you quote-unquote plug in. So this would be the same thing as 1 over x times the reciprocal of the bottom. So instead of dividing by 2x, I'm multiplying by 1 over 2x. So this is the limit as x goes to infinity of 1 over 2x squared. And so clearly this is going to be a situation where I have 1 divided by something really, really big. My answer is really, really small. And again, ln x then grows slower than x squared.